Hi, and welcome to session number 5 of Java Programming 3. As it is already a tradition in my Java classes, class number 5, it is the most complicated one. And mostly it is because I like to introduce, to warm you up to more advanced concepts. And then class number 5 and 6 is just essentially taking you to something that will be a little bit more useful. Not that Java programming is not, but it's more based towards computer science theory and how do we fit in Java into that. So today we're going to be talking about algorithms. And our agenda today is, from a time perspective, is going to be short. From a content perspective, it's going to be loaded. So that means that there's going to be a lot of things to rationalize, a lot of things to absorb. And most importantly, I try to keep the math of the theory to the absolute minimum. So that way I'm not boring you with certain details. So, so what is the purpose of studying algorithms? How do we analyze algorithms? What are the design basics of computer algorithms? What are high growth functions? What is time complexity? What are some example of some sorting algorithms, which are a good that illustrate some of the things that I'm going to be talking about. And last, we're going to talk about merge sort as an exercise, and then we're going to discuss the assignment for this week. Okay, so what are algorithms? This slide, I kept it incredibly simple. It's just an algorithm is a very well-defined computational procedure or steps that receives an input and produces an output. So it receives a set of values as an input, produces a set of values as an output. And in order for us to consider that the album is correct, it's as simple as it produces the correct value. So for any values that it's given, it produces the adequate value. So why do we care about the computer algorithms if computers are fast? Well, we're going to have cases like, let's assume two cases for sorting 10 million numbers and two different scenarios. We have a computer speed that it's really, 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 really fast, a good programming using a poor algorithm, and 10 million numbers. Our case B, we're going to have a computer that it's no average, just regular speed, and programmer, and the same thing, utilizing a better algorithm like merge sort, and 10 million numbers. And in this case, even having a better programming and a faster computer of case A, which the computation is stated here, the algorithm of sorting those 10 million numbers would take about 5.5 hours or 20,000 seconds. In the case of programmer B, where even that you have the disadvantage of an okay programmer and a computer that it's not incredibly fast, it would take 20 minutes. So for those of you that want to do the math of the cost that it would cost you to have a computer rented, an EC2 computer or something like that on AWS or DigitalOcean or something like that, where you have, or Google or wherever you can actually rent per the hour the computer, it translates into money. And that's money that we are leaving on the table, and it's not good. Okay, so then how do we determine that merge sort is actually a better algorithm than insert sort? That is through the practice of algorithm analysis. And what that means is that you're going to be able to predict accurately what are the resources that it requires, be it memory, bandwidth, hardware, time, and even sometimes just, this is not really like the traditional algorithm analysis, sometimes time to develop and maintain an algorithm. If an algorithm is only doing small operations, say like sorting 100 numbers on average, honestly, it doesn't make much sense to put like the most amount of perfection in an algorithm when manpower is much more expensive than computing power in those small cases. The factors that influence the algorithms could be the input size, how many elements we're passing through it, and how long it takes to run. And the input size will actually determine the size of the problem. It's not the same to keep calculating what is the infinite value of pi. And, that's just a small input, but it's constantly recalculating itself into an infinite. Or just essentially sorting 10 million documents, or looking for counting words on those elements, or searching for other type of data. So in the algorithm analysis, often we take into account the worst case runtime. And by that means that when we understand the worst case scenario, we have a limit by which the algorithm runtime will never go beyond. And that's good because it allows us to make like some predictions and something that it's a little bit more, it's going to allow us to make more predictions. So there's also the other concept that is the average case scenario. There's also the best case scenario, and there's the average case scenario. That one is calculated by randomized algorithms to figure out what is to try to sample different input sizes and figure out which one is the average of inputs and outputs of what it takes. So for simplicity in algorithm analysis, we're going to ignore the actual cost of each statement and represent it as a constant. What that means is that if a file takes a slightly longer operation than an addition or a multiplication, if opening a file takes longer than adding a number or subtracting a number or a simple math operation, it won't matter for this context. We are putting all of the small operations into a single cost. We're ignoring how much it will cost us. And the thing that we are interested the most is how much the algorithm grows and scales. And we consider one algorithm to be more efficient if its worst time has a lower order of growth. So meaning something that expands infinitely, that may not be the most efficient thing. That's why you prefer something that has a constant or even smaller runtime than, even though that it may be we consider one algorithm to be more efficient than another if its worst running time has a lower order of growth. So if you have two algorithms that run at about the same time for the same amount of input, but one has a lower order of growth, then we will consider that one more efficient, because that means that when you add more numbers or more inputs or more things to calculate, more words to search, whatever it is, it will grow more in the operations versus instructions, inputs versus instructions executed. So then we're going to review a couple of design algorithm approaches. And one is the incremental approach, which is something that we've been doing without any particular number. It means that as you are understanding and solving the algorithm, you are going to be building a better algorithm each time. And the other algorithm strategy is going to be divide and conquer. That means that you are going to grab the problem and break it into individual small problems and then merge it all together. There's other design algorithm strategies that we're going to review on a second part of this class, which is dynamic programming, greedy algorithms, and amortized analysis. But we're going to leave those for later just because there's quite a decent amount of content to, or concepts to grasp. So for divide and conquer, we have, it's a method. Divide and conquer is a method that divides the problem into sub-problems of the same thing. The conquer phase is resolving them in smaller chunks recursively. So as you are starting from a problem this big, and then you're going to say grab half of it and work on that, and then from that you're going to recursively grab half of that and work on that, and then recursively you're going to grab and work on that other half, and so on until you have two elements, for example in the case of merge sort. And then the combined section for the step of divide and conquer is going back into the algorithm once you solve the individual smaller pieces. That is called recursiveness, the concept that it lies behind it. That means that you're calling the same function from within itself. So you are, but for a different type of input. So let's say we have 10 numbers and we're talking about the merge sort algorithm. And in the merge sort algorithm, let's assume that we have an input of, let's get rid of the ruler. Let's assume that we have an input of value. So we have 1, 3, oh, what kind of number is that? 1, 3, 4, 8, 7. I'm new with this tablet. 6, and then we are going to do like say 9, 2, 5. So we have that array of numbers. Let's just separate it by grabbing a different color, and let's say I want to grab the red just to separate them from each other. And let's assume that we have those values and we want to separate them to solve the problem. So in a divide and conquer, we would grab this side and then call the same function recursively with only this inputs. So then the next step, it would be using 7, 6, 9, 2, 5, and only for those 5 inputs we're going to resolve the problem. And in a proper divide and conquer, we would call the same function again, but dividing it in half. We would have 2 calls, one for 7 and 6, and then the other one for 9, 2, and 5. And then we would keep calling it until we solve whatever problem that we have at the bottom level, and then we start returning the values to be processed until we are back at the top resolving the main problem. So that's more or less like the divide and conquer strategy. And let's say that we want to just to talk about recursiveness. Let's create a new project, and I'm just going to create a new regular Java command line program. Let's talk recursive, or let's go Java 3 class 5, our single, our same project. So we have now this guy here, and let's talk about recursiveness. Recursiveness is a technique that you use to call a function on itself in order to solve the problem. And in the past, we did something like this to calculate Fibonacci numbers. So so we loaded. So in the past, we did Fibonacci like this, but I kind of want to do it in a new way in this new project using recursiveness. This actually uses a heavy memory set because it's keeping the counter and essentially a lot of the variables around, and it just it's a different way of solving the problem. So from a recursive way to solve it, let's say, and let's copy the same signature. So we're gonna just grab this guy, and we are going to then, in this, we're going to, I think we are going to, no, here it is. We're going to create our test, so that way we execute it. Yes, we're going to test it. We're going to use JUnit5, and we're going to use our getFib method. We're going then to enter this guy to add IntelliJ, and we're set. So now we can start calling Fibonacci generator dot getFib. Let's make this into static, so that way I don't have to instantiate anything. GetFib, and what this signature, what we had here, is that we were going to pass the position of the Fibonacci number that we were going to generate. So let's say that we're going to get the nth number, and in the same way that we did it before, if we Google this Fibonacci sequence, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So we should get 34 if we start counting at 0 or as a Fibonacci number. So let's say that n, we should get, actually let's do assert equals, assert equals, we're going to call this guy, which is the expected, which is 34, and this guy. Okay, so let's write it in a traditional recursive way, and what we are let's do this getFib recursive, and let's copy this guy here just to also compare both, and let's change this to also static, so that way we don't have to create an instance. So we're going to compare our Fibonacci recursive against the number 34. So in a Fibonacci this, we're gonna essentially, we're going to be calling the bottom of the stack until we do something like get fib recursive, and let's call it n. Well, position -1 plus position get recursive position -2. Now this brings a problem where if the position is either 1 or 0, which if n is less or equals than 1, oh no, it's not n. If position is less or equals than 1, then we're going to return position. And this is a traditional, let's just remove this guy here. And if we run, this thing is gonna finish, ooh, actual minus 34. So I think, oh yes, we didn't do the position minus. So let's go again. This is where TDD actually helps us. Yeah, so we have, when we have the position greater, less, or equal than 1, I don't know why I didn't type it right, then it runs correctly. Now let's do another, let's call this like get fib recursive, and then let's do the same thing for our other get fib, and let's say get fib for this guy. So now let's run the non-traditional, the non-recursive way, and we're also getting the same result. This is more the incremental way. This is the divide and conquer. So let's discuss what we're doing here, and let's run this by hand, and let's say that we're going to do the 6th number, which is 8, and we can just verify that just real quick by going into a really simple thing. And we can verify that by going into Google and like just real quick looking at this table, which has, like I just put Fibonacci sequence, and it has 0, 1, 2, 3, 4, 5, 6. So the 6th number is 8. So I'm gonna have it just run my test, make sure that it runs correctly. So yes, 8 is the 6th number, and let's run it by hand just to make sure that we are getting the right value, just to verify this algorithm. And it's fine if you don't get like how do you design some of these algorithms on the first try. As time passes by, just the fact of calling the same function from within of the function. So this function is calling our same function. That's called recursiveness, because it's going back into the same function with a different value. So let's assume that we start with the 6th position, which is this guy, the long position, and then we're going to start going into drawing our little tree with calling our recursive of position -1 and position -2. So position -1, the first one is going to be 5, and then position -2 is going to be 4. Then this is going to break it further down into, and let's just go into our arms a little longer here, so that way we are sending this value. N, which is 5 minus 2 is 3, and n minus 1 is 4. Then we have 2 and 1, and we have here it would be n minus 1 is 3, n minus 2 is 2, and then 2 and 1, and it stops right here because we are saying that if it's less or equal than 1, then it just returns a value, so it stops right that. But this guy can continue further down, and it's 1 and 0. The same case is here. We have 1 and 0. Same thing here where we have 1 and 0. So every time that we have the 2, we will get like a 1 and a 0, a 1 and a 0. Here it's the same situation. It's going to be 3 and 2. Then here it's going to be 1 and 0. And then down here it's going to be 2 and 1, the same tree that it's drawing here, and then a 1 and a 0. And what I'm going to do, just to differentiate the results and the ones, so let me just draw these ones better, so that way my lines from the tree don't confuse anybody. Just put all these guys here. So we have our tree that was drawn by hand, and we are going to then start adding this guy for this plus this equals 1. So I'm going to put in green the number of the result,
this plus this equals 2, and then this plus this equals 1, 2 plus 1 equals 3, and then here 1 plus 0 equals 1, 1 plus 1 equals 2, 3 plus 2 equals 5. So this side of the tree, we've resolved it to a 5 by going recursively, and then we're going to go and do the same thing again. 1 plus 0 equals 1, and then 1 plus 1 equals 2, then 1 plus 0 equals 1, 2 plus 1 equals 3, so 5 plus 3 equals 8. And that is how recursively we solve the function. Not only the code is a little bit more elegant because it's one thing, something for another, but in this case it becomes a little bit less easy to read, but it's much more efficient and much more elegant.
So since we were talking about recursion and stuff like that, now let's talk about recurrences. A recurrence is a math equation that describes the function runtime in terms of its input. And the way that we can actually solve that recurrence is the substitution method, just essentially going and brute forcing and replacing every one of the equations of the recurrence. We can try to do a recursion tree method, which is essentially what we just did with where is it? This guy, where we were building our recursion tree method and a master method that only works for a certain particular set of recurrences. And right now, because that is too much math, because it has a very specific formula, I don't want to go into that without having a proper math explanation. So since this is not a math class, it's a Java class, I'm just going to say that's the master theorem. We're not going to touch it for now. Just trust me that is the case. But recursion tree method is probably like the easiest, or the other one is just essentially solving it by substitution. So then let's talk about what are some of the functions that we use to measure the growth of functions, and that is called an asymptotic function. And an asymptotic function, I don't know if you've ever seen like a graph of, say, a logarithmic function or an exponential function, that it's a function that tends to go to 0 but never really touches 0. So if we go and then let's don't save this. Let's assume that we have, let me get a different color. Let's go for a black here, and then let's go and have our x. This is our x, and this is our y. X. Let's do a better x here. An asymptotic function could be something like this, that it never really touches 0, or it never goes into one of the axes. So some of these asymptotic notations, they describe the algorithms in the amount of space or time that they utilize. And some of the most common ones, it's theta notation, omega notation, or O notation. And this is where we get into the topic of the theory of big O. And I can go into the math, super deep math side of it. I just wanted to distill it into like something simpler, such as what does it mean? And we have like the big O notation describes the upper bound of how much. It's a function that describes an upper boundary of how much that function would take to run. So in this case, if we are, and let me just, how do I remove this guy? Okay, so that way we have a little bit of extra space. Let me zoom in a little. Where's the zoom? Let's fit slide. Yeah, a little bit better. Okay, so this function here, for the most part, is essentially saying what is the biggest, the most time that this function, given different inputs and different things that it can take. And usually that is what it's called the big O notation. From a math perspective, it just essentially means a function that is bounding the other function on an upper limit. So theoretically, I mean, in this case, it could go a little bit higher, but as it scales, this will give us a guarantee that it won't go up past a certain value. However, we're never really going to be describing how tight this function is going to be close to the other one. So, in a calculation of big O notation, because we're not really going into the very specifics of how much is the cost of a function, we might be actually over calculating something, but at the very least it gives us an idea of how much it is. So the idea of the big O notation, when somebody speaks about big O, is that they're describing what is the worst case scenario for that function to run. Similarly, the big theta notation is the lower bound. You can see it here in green versus the one in blue. The one in blue here is our function. The one in blue here is our function. The one in red here is the upper bound in big O. The one in here in big theta is the lower bound, or the best case scenario. And then if you want to know both limits, then you describe the function in terms of a big theta notation, which is essentially big O and big omega both at the same time. Just in a very, 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 very simple matter. That's the easiest way to think about it. Big O is the upper bound, or the worst case scenario of the runtime of an algorithm, or the resources that an algorithm is going to use. Big omega is the best case scenario, and big omega, big theta is the both. It just represents both the best and the worst case scenario, or the space that function is going to run. Now, if we wanted to try to find out the average, because one thing is knowing like the best case and the worst case, but if we wanted to know more or less like the average, there's another technique that you can use by generating randomized values and then executing some of the time to figure out what is more or less like an average time that it would run. And obviously the average time, it is more related to somewhere in between the big theta values. Now let's describe a little bit of how time complexity would work in both cases. And what I mean here is that what I want you to see is the number of operations n, which is the one on the y-axis, the number of operations versus the number of inputs. So in the case, as you can see, you can process more operations given the number of inputs in the ones like the one that is in pink, purple, and teal. The one that is in green, it's executing the same amount of operations versus inputs. That's n, that's linear. That is called a linear function because it's essentially representing a line that it's 1 to 1. In the case of also the pink one, it's a linear function because it's just horizontal, and that means that it's a constant cost. A constant cost is essentially 1. And a good example of a search algorithm that has a cost of 1 is in a dictionary or a hash map, where you are only doing a constant value of operations. So that means that doesn't matter if you are passing it 300 elements to search, it's going to resolve it in the same constant amount of time. It doesn't matter if a hash map has 800 elements and you're trying to search a number in it, the search operation will be a constant value of 1. Algorithms that are linear, that means that they're doing the same. They're taking in the runtime, best case or worst case or whatever is the one that you're analyzing. It's going to take the same amount of operations. It's like finding an element in an array the worst case scenario is that it's going to take you n elements given the array. And the worst ones is where it's exponential. So for example, n squared or n factorial, those essentially you can see that given the amount of input for each function, the cost or the number of operations will spike dramatically and not process very much. So you can see that here, for example, these guys are not processing a lot, but actually are processing a lot, but accomplishing very little. Okay, so this is another example of a divide and conquer algorithm. We did the Fibonacci code, but I want to go through the merge sort. The merge sort is an example of an algorithm that has a runtime of n log n runtime, and it's the idea is that you're going to have an array of elements and you're going to sort them. So in a merge sort, you're going to divide the elements until its smallest inputs. So for simplicity here, I didn't fully go ahead and like started to break it down into like from the idea is that you divide the algorithm in half. So in reality here I should have added like an extra step that would be 5 2 4 6, and then another one that would be 1 3 2 6, then another layer that would have 5 2 and 4 6 and 1 3 and 2 6, and then those would be broken down into this layer. But the idea is that you first break in half, then break in another half, then break in another half until you have individual elements. And then you start applying a sort of those elements. So for example, which one is smaller between 5 and 2? Then it would choose 2 as the first element and then 5. And then between 4 and 6, which one is the smallest? Then it would keep it 4 and then 6. And it brings it down to this level. 1 and 3, 2 and 6. Okay, so this up to this level, each one of these subarrays are sorted. Then between these two guys, it would start for each number. So which one is the smallest between 2 and 4? Then it would choose 2. Okay, between 5 and 4, it would choose 4. Then between 5 and 6, it would choose 5, and then 6, because that's the last one. In the case of these two arrays, it would start with 1 and 2. So it would bring down the 1 because it's smaller. Then it would compare 3 and 2. So it would bring down these 2 because it's the smaller one. Then 3 and 6. Then it would bring down this 3. And then 6 because it's the last element. And then we have another merge operation to do. After we did, you can see the division. This is the divide area, getting to this point, and then the conquer is each one of the sorts, and then the merge is part of that, like bringing it back. So now we have two subarrays, 2 4 5 6, 1 2 3 6. So we're going to be comparing 2 and 1. We're going to bring down 1, then 2 and 2, doesn't matter. It's going to bring either of the two 2s. Then 4 and 2, it's going to bring the 2. Then 4 and 3, it's going to bring the 3. Then 4 and 6 is going to bring the 4. Then 5 and 6 is going to bring the 6. Then 6 and 6 is going to bring down the other 6. And that's how you'd perform a merge sort. Here's a little table that it's quite handy to remember, and this is actually a Google interview question in some cases. Like they particularly ask you, what is the runtime of certain algorithm method? So you can see that the worst one is insert sort, because it's having a worst case runtime of n squared and an average runtime of n squared. Merge sort is, if we compare it to this table, from n squared to n log n, well, there's already some progress. And then quick sort, the worst case scenario is n square, and the average runtime is n log square. Counting sort is k plus n. Radix sort is n plus k. Bucket sort is n square n. In Java arrays, in the Java arrays packages, there are two versions of sort that are implemented. One is quicksort for just primitive types, and uses merge sort for things that are using a comparator. It's very typical for programming languages to have the built-in default sorting algorithm to be merge sort, just because it's one of the ones that performs decently in mostly every scenario. So this is the algorithm of merge sort, and we're gonna find the middle point to divide the array into two halves. Then we're gonna call the merge sort for the first half. Then we're gonna call merge sort for the second half, and then we are going to merge the two halves and return that to the stack. So let's go ahead and create a merge sort class. We're gonna Java class merge sort, and we are gonna also add our test, and then we're gonna call it merge sort test. And back, I gotta get a better seat. And so we're going to do a public static int. We want to get an array of ints, merge sort int data. We're going to pass an array, and we're going to get another array that it's sorted. So I'm going to merge our values into our new int array that it's going to be the size of the original data, where it's just going to be the same thing but just sorted back. And we're going to then say that if the data dot length equals 1, then we return data. Why is that? Because when we start dividing the algorithm, and this is where I've got to go back to our slide, I stop dividing once I get into elements that are just 1. So once I get into, for example, here, the array length is 1, the array length is 1, the array length is 1, etc. So I'm going to be dividing until I get the array 1. Also, the algorithm, if we go into this guy, it says that we have to find the middle point to divide the array into two halves. So we're going to do middle, or let's go, middle point equals data dot length divided by 2. At this point, we know that it's fine if it's 2 or more, because here we're escaping before we get to this division, so we run the risk of making mistakes. We don't run as much risk of making mistakes. Then we're going to get a sorted array for our first half. So I want to do merge sort on a subarray, and the way that I'm going to call the subarray is I'm going to use the arrays Java util, and then let's do copy of range, and we're going to pass our data array, and we're going to go from 0 to the middle point. So from 0 to the middle point, and then let me just put it like this. And then int sorted b equals merge sort from arrays, copy of range, data, and then from the middle point till the end of data.length. Basically, this is the second side of the array. No, these are both arrays. So we're getting the first thing that we're gonna the first part. Let's call it first part, and then we're gonna call it second part. So we're dividing it in the middle, like the algorithm, like the pseudocode said. So if we go back to this guy, we find the middle point and divide the array into two halves. So far, this is what we've got. We got the two arrays divided into two parts. So in our array here, we start going, and let's go into something a little bit more complex, like this guy, that it's not as simple as these guys, because you can sort each one and then merge them together. But what we want is a case where you have a number where 2 and 4 need to get into the array. So what I'm going to do is that I'm going to put two indices for these two arrays, right? So I'm going to do index, int index of 1 and index of 2. And in both cases, I'm going to start them at 0, because that's where I'm going to start essentially counting from 0 to 0. So I'm going to have index of 1 and index of 2. And I'm going then to iterate over my data length, which is the size of these two guys here. So for int the index, where we're going to be the index of this array, right? We have, when we're returning the function, this is a little difficult to see, but when we were returning from the initial part, we have our data array that it's the length of 4. So we're going to be iterating of the size of what we want to build. Here's another way of doing it, so that way it's less confusing. Until index less than, let's just call it first and second. First dot length plus second dot length. So we're going to be concatenating those two. So while the index is less than that, then we're going to be incrementing. So we're going to repeat this for loop as long as the first and the second array are still being happening. Okay. So what we want is to find the minimum point between both of these guys. And so we're going to do first, and then we're going to get ideally, this is one thing that int a, the first one that we're going to put, is going to be the first value 1. Let's call it value 1. Int value 2 equals the second, and then we're going to do of index 1 and index 2. So we're extracting those, and I know that at some point we're going to get a index bounds array, because you might have like an odd number of entries. So we're going to address that in a second. But right now what I want is then to say that the one that I am going to sort is going to be math.min. I'm going to grab the smallest one of the two. Which one is the smallest of these two numbers? So we're going to get the value 1 and value 2. And depending on which one we choose, so if sorted equals value 1, then we advance the pointer of value 1. That means if I chose this one, then I'm going to advance the pointer of this one and leave the same one here. So it's going to be the pointer of the first array here. The pointer of the beginning of what we're analyzing is going to remain here, because this is the one that we chose. So we're essentially like putting it down and keeping our finger like this. I don't know if that makes sense. Like, we are analyzing two arrays with two indices. So we have this guy and this guy. Which one is the smallest? This guy. So we're going to put it down, and we're going to move our pointer to here. So we have our index now, it's on this guy, and we have our index for this array on this guy. So we're going to be comparing 5 and 4 on the next item. So because we found that the sorted was the one from the first value, we're gonna push our pointer just like we explained in the chart. Otherwise, because if we don't choose one, then we're choosing the other, we're gonna increase the second pointer. That means that if the smallest one, in this case, for example, 3 and 2, which one is the smallest? Is this guy. So we're gonna advance the other pointer. So this is just helping us to move the pointers onto the array so we can do the comparison. And then in the merged value, we're gonna do in the merged index, IDX equals sorted is a sorted value. So if I was going to then go into our merge sort test, oh, we gotta return the merged. We're gonna return our merged value like this, right? So if we're gonna be doing this guy, let's just call this the same method. Public void merge sort, and we're gonna also decorate it with a test. So we can now do merge sort dot, wait a minute. Oh, I put the values backwards. So I'm gonna move this guy here. Sorry about that. Yes, and we're gonna move this function into the test one. Sorry, I put the values into the incorrect class. I coded all that, but I can just copy paste it. And we're gonna remove this guy. We have our test merge sort dot merge sort, and we're gonna do a new array that it's 5, 4, 7, 6. Actually, let's just take it out so that way we have int values. It's an array that it's this guys. So then we're gonna pass values. And there we're, ta-da. And I wanna just print out whatever. And actually we're gonna need arrays to string, so that way we convert the return of the result of this guy into string. And let's just run it. It's gonna crash because it's gonna have an array index out of bounds exception. And that is because at some point we gotta add a mechanism for line 23. That means that one of these two arrays, at some point, we're gonna continue looking at the data. For example, when we go into 2, 4, okay, we bring 2, then 5 and 4, we bring 4, 5 and 6, we bring 5, and then once we move the pointer, this guy is empty. So what we gotta do is that we gotta add some code that catches that situation where the pointer of the array is bigger than the length of our array. So what we're going to do is that I'm going to take int value 1. I'm gonna take those declarations out, value 2, and in both cases I'm gonna do integer dot max value. And the reason why I'm doing this is because I am going to compare whatever maximum value that integer, which is 214743867, to whatever value that we have in the array. So whenever we're getting the math minimum of that super high value versus 6, so this guy's going to return that super high value after once we go in here, and then 6, which one is going to be the smallest? This one. So it's gonna work out, and then we're gonna then add a couple of exception catching here, where we're gonna say if value first dot length is less than is greater than, if the length is still greater than our index 1, then we catch that value. If second dot length is greater than, so if an array is bigger than what we're trying to point at, then we also add this guy. And we go back, and ta-da! We have 4, 5, 6, 7. An array that is actually sorted. These two codes, the one of the Fibonacci generator and the merge sort, are going to be uploaded in the code of the class into the GitHub repository, and you guys can look at it and analyze it and play with it. As far as the exercise that we're going to be doing is that we're going to be calculating a factorial. And a factorial is nothing else other than it's represented like this, and what it means is that it's going to be n times n minus 1 times n minus 2, n minus 2 times n minus 3, all the way down to a multiplication by 1. So this is another example where we can use recursion. And what I will want is that you guys submit, and I have it written here. What I want you guys to submit is the code, the unit test for that, and also your big O notation of what is the worst case scenario of your analysis. You know, what I'm expecting is something similar, or a calculation similar to any of these functions. I don't want like something fancy. I just want, you know, something that it says, oh, it's n squared, n log n, or something like that. A good way of determining if something is, say, for example, n squared or n, if you're doing a for loop, most likely you're in the n category. If you're doing 2 nested for loops, you've already gone into the n squared category, unless you break before that and then you start decreasing. You start going from here to here. Anyway, I'm looking forward to seeing what you guys come up with.